Okay, so we've now defined what is meant by non-spherical errors, and we've looked at two problems that occur in practice, heteroscedasticity and autocorrelation, and we've talked about how we can detect them. In this part of the lecture, I now want to turn to a general solution that's called generalized least squares, which we can think of as a generalization of the least squares estimator to account for problems in which non-spherical errors are present. So let's just set the scene again by thinking about what this Gauss-Markov 2 assumption actually means. So recall from lecture 5 and 4 actually, that under the Gauss-Markov theorem, the least squares estimate is the best linear unbiased estimator. It's blue. So it's unbiased with expectation beta and its variance, sigma squared times x transpose x inverse, is the minimum variance achievable among linear unbiased estimators, the minimum variance in the class of linear unbiased estimators. So what are the theoretical implications when the actual error variance is sigma squared big omega rather than sigma squared I, which is what we want? The answer is that the least squares estimator will remain unbiased, but it becomes inefficient. First, unbiasedness. Violation of the variance assumption doesn't change the form of the estimator. So the the OLS estimator beta hat is still x transpose x inverse, x transpose y, which we can write in this form here as beta plus x transpose x inverse, x transpose epsilon. And this is unbiased as long as the exogeneity condition holds. That is, the errors of zero mean independent of x. The estimator is still unbiased because this term here is going to disappear. However, when we compute the variance, we now have to plug in sigma squared omega for the error variance, and we end up, when we do that, with this Simage expression at the bottom of the slide, shown here, sigma squared times x transpose x inverse, x transpose omega in the middle, x transpose x inverse. And that is no longer minimum variance. Least squares under those conditions may be inefficient. And as a second, arguably more serious consequence for our inference, our usual estimate of the variance of beta hat, which is s squared x transpose x inverse, is now generally biased and will lead to incorrect inferences potentially, invalid standard errors, t-statistics, f-tests, and confidence intervals. So the question is, how can we fix this problem? Well, to see how we can fix this, suppose that omega is actually, big omega, is a known positive definite matrix. If that's the case, then we can find an n by n matrix V such that V transpose V is equal to big omega inverse. So if we know this, we can find this matrix V. Now here's the idea. We use V to transform the regression model. Multiplying through by V would give us Vy times Vx beta plus V epsilon. Okay, so V is equal to, we can write it in this expression here, and V omega V transpose is equal to the identity matrix. So we take V and we transform our regression model by pre-multiplying it through by V. What are the properties of the error term in this transform model? Well, its expectation is V times the expectation of epsilon, which is 0. And so, V is a matrix of constants, so it comes out of the expectation. And its variance is V times sigma squared omega times V transpose there, right? So it's variance, apologies, V times sigma squared omega V transpose, which by construction equals sigma squares times the identity matrix. So this is the important point. The variance of the error term in the transform model gets back to a variance that is spherical, and it does it through this little bit of algebra here. So in other words, the transform model meets the Gauss-Markov criterion. The expectation of the transformed errors is 0, and it has constant variance. And therefore, if we apply least squares to this transform model, it must be best linear unbiased estimator by exactly the same proof that we used in lecture 5. And this estimator is called generalized least squares, denoted beta hat GLS. And GLS is simply least squares applied to the transform model that satisfies the Gauss-Markov assumptions. But crucially, the transformation must be for a known positive definite matrix transformed by V, where this relationship here holds. That's how generalized least squares works. So let's write this down formally. The generalized least squares estimator, the GLS estimator, is the least squares estimator computed on the transformed data, Vx and Vy. Applying the rules of matrix algebra and using V transpose V equals omega inverse, it simplifies to the expression at the bottom of the definition. Beta hat GLS is equal to X transpose omega inverse X inverse times X transpose times omega inverse times Y. That's the expression that we get to for beta. The variance of the generalized least squares estimator is sigma squared times X transpose omega inverse X inverse, and the theorem states the key result. Since the transform model satisfies the Gauss-Markov criteria, GLS is the best linear unbiased estimator, and its variance is at least as small as the variance of the ordinary least squares estimator applied to the untransformed model. So formally, the variance of OLS minus the variance of GLS is a positive semi-definite matrix. And you could prove that in your own time just by a straightforward piece of matrix algebra on the definitions that I've given. So this is the generalized least squares estimator here. It's important, by the way, as a solution, of course, to non-spherical errors, but we're actually going to use it in a later lecture, lecture 8, when we look at mixed models. So it's a generalization of least squares on a transform model. Now, what about inference? If the errors are normal with variance sigma squared omega, then the GLS residual vector is the residual from the transform model. That is Vy minus Vx beta hat GLS. That's the residuals that we calculate. And we can use it to form an unbiased estimator of sigma squared, and that's given on the slide. It's the usual residual sum of squares over n minus k minus 1, computed with omega inverse in the middle. And statistical inference from the model parameters for the t statistics, the confidence interval, the f statistic, etc., can then be calculated just as in the case of the normal linear model, but using the transformed variables. And since the transformed model satisfies all of the assumptions, all of the inference machinery from lecture 5 carries across directly, and we end up with good, valid inference from generalized least squares. Now I want to make two further distinctions in relation to GLS, specific forms of GLS, and the first is called weighted least squares. This is an important special case of the generalized least squares model applied to the heteroscedasticity problem. Now, as we noted earlier, under heteroscedasticity, omega is diagonal, as shown here. Now, if we can determine a set of weights, Wi, equal to the reciprocals of the diagonal elements omega I, then the GLS estimator is referred to as weighted least squares, and it's defined in this definition here. And the definition writes the estimator as a weighted sum. The inverse of the weighted sum of xi transpose times the weighted sum of xi yi, just to emphasize how the weights enter the computation. And the logic of the weighted least squares estimator is that observations with smaller variance receive a larger weight in the computation of the sums, and therefore have a greater influence on the estimates obtained. Observations we measure precisely count for more, in other words, noisy observations count for less. In effect, the weighting cancelling out the heteroscedasticity that we observe in this diagonal part of the omega matrix. Okay, so weighted least squares just being a particular form of the GLS estimator. Second distinction that I want to make relates to what we call feasible generalised least squares. Now, for both GLS and weighted least squares, we've assumed that omega consists entirely of known elements that can be employed directly in estimation. For instance, we've assumed that we have these WIs that we can just plug in. But in practice, the elements of omega are typically unknown, and estimation therefore has to proceed in two steps. In step one, the unknown elements of omega are estimated, usually via the OLS residuals. In step two, the estimated matrix omega hat is used in place of omega. And this two-step process is known as feasible generalised least squares. So we don't know, so all we're saying is we don't know omega, we're going to estimate it, and we're going to plug that in. And we call that feasible generalised least squares. Feasible in the sense that it's not the theoretical generalised least squares, but the version that we can actually compute with the data. Now the estimator has the same form of GLS, but with omega hat substituted for omega. One technical note, the fact that omega hat is random introduces complexities in finite sample analysis, so FGLS is usually evaluated via its large sample properties. So how do we estimate omega? In practice, some structure must be imposed on it, and this is typically achieved by estimating a small set of parameters p such that omega is a function of p. And we've kind of hinted at this earlier on when we mentioned heteroscedasticity in the formal testing. But for heteroscedastic errors, a typical model sets sigma squared I equal to sigma squared times h of xi and delta, where h is an exponential function of the explanatory variables. So the covariates determine the pattern of heteroscedasticity through a small number of parameters, delta. For autocorrelated errors, a commonly used model is the AR1 process that we've already met. In this case, omega is specified as a function of the single parameter rho with the structure shown on the slide, ones on the diagonal, and powers of rho on the off diagonal decaying as observations get further apart in time. But what if the form of omega is misspecified? Generally, it won't introduce new problems. It simply fails to address the problem we intended to resolve, so our inference remains incorrect. There is one exception to that. When not all x variables are strictly exogenous, the OLS remains consistent, but FGLS in general does not. And I've included a proof of that for those that are interested on the next slide. I'll sketch out the logic actually of this slide, and you can work through the algebra in your own time. So the OLS estimator is consistent if the expectation of x transpose epsilon is 0. For FGLS, we write the estimator in terms of sample means, as shown in these equations here, and we apply a law of large numbers. The result is that for FGLS to be consistent, we need the expectation of x transpose omega hat inverse epsilon to be 0. And that is a different and stronger condition. It will not necessarily hold under the basic exogeneity assumption that x transpose epsilon has 0 expectation, because omega hat inverse reweights and mixes the observations. That's why, under weaker forms of exogeneity, OLS can remain consistent while FGLS does not.